Hey, this is the solution to extra credit number 2. I believe it's number 2, 1 or 2, but it's the chess problem with the castles. And again, I'm going to show you 2 ways to do it. The problem itself says that we have an 8x8 chessboard with this one particular square blocked out, and we want the probability that if we place 8 castles in those remaining 63 squares that they won't be able to hit each other. So the problem boils down, it's pretty easy to find that 63 choose 8 is the number of ways we can place them. Question is, how many ways can we place them so that they can't hit each other, knowing that we have this barrier here now. So we could potentially have one down here and someone still in this column, or one here and one over here in the row. The difficult part here is choosing cases. So I'm going to show you one way to do it, and I'm actually going to show you 2 ways. The second way I think is more artistic, and that was actually found by 2 of the students in the class. So notice here I've labeled a few different zones. I've labeled this special spot as 1 right here, and a spot right here as 2. 3 means that there would be a rook somewhere in this green zone, and 4 means either somewhere in this final column other than this one spot here. So that's my 1, 2, 3, 4. And then I develop my cases based on those 4. So for example, following this line would be the cases where there is a rook on 1. Following this line would be the ones where there is not a rook on that number 1 spot. If there is 1 on 1, we could say there is 1 on 2, or not 1 on 2. In other words, that special spot here in the 7th column. And so on, 3 and no 3. Notice we don't even have to consider 4, because if there is 1 in 3, there cannot be 1 in 4, because that would give us 2 rooks within the same column that doesn't even have a barrier, which is certainly not a solution. But let's go through just one of these maybe, and I think you'll get the idea of what's going on here. So following this, we have a rook in 1, a rook in 2, a rook in 3. So that means we have 1 in this special spot, 1 in this special spot, and then we do have 1 in this column right here. So we have 3 rooks placed so far. Notice now we have all these first 6 columns left to place 5 rooks. So how many ways are there to do that? Well, there's 36 possible spots, right? Because this one is not taking up a row. In other words, we could have another rook in this row, but the number 2 is blocking out this row. We cannot have another rook in this row, and wherever we choose the rook for 3, it's going to block out that row. So there's going to be 2 of the 8 rows blocked out. That leaves 6 rows, 6 columns. 6 by 6 leaves 36 positions where we could place that next rook. Once we do that, it'll block out a row of 6, a column of 6, leaving us with 25, and leaving us with a 5 by 5 grid of options, then 4 by 4, 3 by 3, 2 by 2. However, this is going to give duplicates, because these 5 rooks could be placed in any order, so to get rid of the duplicates, we divide by 5 factorial. And then the total number, I labeled this 1. Notice that option number 3, there were 6 different places that I could have placed it in the green right there. Whereas 1 and 2, you either have it or you don't. 3, there were 6 different options. So I multiplied 6 by this right there, that quotient, and that gave me 25,920 possibilities for that option 1. And I will try to attach this PDF so you can look at it without scrolling if you want. Similarly, we can go through. I did want to go through at least one where we didn't have to worry about duplicates. So let's look at this one here. No 1, so there's not 1 right there. No 2, so there's not 1 in that special place right there. But we do have 1 and 3. Okay, so we don't have 1 there. We don't have 1 here. We do have 1 and 3. Notice that this is 6 times 6 factorial. Why 6 times 6 factorial? Well, first let's choose the one here on this far column. We have 6 options. Why 6? We know that there's not 1 and 1. We already determined that when we took this path. And we also know that we've chosen one of these so that one of these rows is going to be totally knocked out to the final column. So that takes out that one and that one, leaving 6 options there in the final column. Once we do that and we move over here, notice that we have 6 factorial. It's just a matter of 6 options for this one, then 5. Now how do I know that I have 6? Why couldn't I have another one in this one right here? Absolutely, I could, and I will. But actually, I shouldn't say that I will. But I have one of these green, which is knocking out a row over here, and something here other than the 1. Remember, I don't have a 1 here, so wherever that other one is, it is going to knock out a row also. So because of that, there would be 6 left over. I guess another way to say that is, even though I haven't chosen this 1, I know I'm going to have 1 in this column. Why? Because I don't have 2 in this column. So as soon as I don't use that special 2, I have to have 1 in every column. As soon as I don't use this special 1, I have to have 1 in every row. Now if I do use this, there can be a column without. If I do use this, there can be a row without. But if I don't use it, then there has to be 1 in each. So anyway, totaling those 7 different cases up, we get 117,000. And I had actually made a mistake the first time I calculated through, and it was caught when I went through this second method where a student divided it into 4 cases instead of 7. So the way they looked at it was, in case 1, each row and column has 1 rook. So despite the special spot, every row and every column has 1 rook. And if you calculate that out, maybe choose this column first, you'd have 7 choices, and then from then on out, you would have 7 factorial. Case 2, the special column has 2. In other words, that one right there, that one right there, but each row still has 1. Case 3, special row has 2. Each column has 1. And finally, case 4, the special row and the special column both have 2. And you can kind of do this like a logic puzzle if you've ever seen these. So, of course we know if we need 2 in the special row, we have to have that one. And just pick an arbitrary one over here. We have to have this one, pick an arbitrary, shade anything that would now be impossible, and you can quickly see that there would be a 5x5 grid there. Okay, so totaling up those 4 cases, you also get 117,000. 63 choose 8 would be the total number of possibilities. Divide those 2 numbers, you get a little less than 3,000th of 1% for your percent chance of success. And again, I'll attach the PDF so you can see that. Okay, the final problem, part A and B, was the soulmate problem. I find it easiest to do doing some kind of graph here and then calculating the area underneath. So here is, on the x-axis, is the minutes after 7 o'clock that you come to the sauna. Notice 55 is the last time you can come. You can't come after 7:55 or you wouldn't be able to stay 5 minutes in the sauna. So it's not 60. What I chose to put on the y-axis then is the probability of meeting. So notice if you come right at the beginning, you only have 1/11th because there's 5 minutes. There's a 5-minute time frame in which the other one could come out of 55 minutes worth of starting times. So 5 out of 55 gives us 1/11th. Whereas once in between 5 and 50, you have a better chance of meeting because they could have gotten there before you or they could come after you. In fact, you have a 10-minute window out of the 55, so 10/55 gives you 2/11. From there to there, it's just a uniform. At the beginning and at the end, we have a linear function. And however you want to do, you can calculate the area. Notice that in retrospect, when I was calculating the area, the x-axis, I was converting to the chance of actually getting that time frame. So in other words, between 0 and 5, this wouldn't be a distance of 5, it would be a distance of 1/11th, because this occupies 1/11th of the possible times for me to come. Between 5 and 50 would be 45 out of 55. So using that, we can calculate the area under this curve and get 0.174. Another nice way to do it would be having the time you come on the x-axis. In fact, you could even just leave it in terms of the minutes. You don't even have to convert it to proportions like I was doing there. And on the y-axis, you could be the time that the soulmate comes. And then you can shade in a region where you actually meet. You can create a region, and from that, it turns out to be a rectangle, or actually a square with two triangles subtracted to get that same answer. It turns out to be quite a bit more difficult when you add in this last third person, this matchmaker. So in this case, we have between these 2 points, it's still relatively similar. We'd have a 10-minute time frame in which our soulmate could come. So that's either yes or no. That's a 2/11th chance. And then we have a 10-minute time frame in which the matchmaker could come. And that would also be a 2/11th chance. So we would just square that to get the chance of both of them happening. And that would be 4 1/21st. So that's that uniform right there. What is different is during this time frame, it actually becomes, it's not a straight line, it's a quadratic function. And you can do this if you plot an arbitrary x here in between 0 and 5. You can see that we're not going halfway. In fact, I don't think I saved, I did this in GeoGebra. So any way you want, you can take these points, you can calculate as many points as you want here. Once you have 3 points, you can determine a quadratic function, which this is an estimate of the quadratic function that it is. And then just integrate that quadratic function from 0 to 1/11th. And then double it, because you're going to have a symmetric area over here. Calculating the rectangle, of course, isn't a big deal, but this does get a little bit complicated because we have to figure out what that function is in order to integrate under it and get that area. So once you do that, it works out to 0.0304. And you might think, well, if we just took this number and squared it, so the chance of meeting soulmate is this, the chance of meeting matchmaker is this, so if we just multiply those two, we should get the chance of meeting both of them, correct? No, because it's not independent. And this sounds a little weird because it kind of depends what we mean by independent here, but if we did meet our soulmate, for example, now we are slightly more likely to meet the matchmaker. Why? Because if we did meet our soulmate, we're slightly more likely to be in this area than in one of these areas. So in other words, it's slightly more likely to be we came between 7:05 and 7:50 versus one of these little zones out here. So because of that, it raises the probability just a bit, not too much, but just a bit over this number squared would be the probability of meeting both of them.